Good afternoon, ladies and gentlemen. My name is Ben Ahmed Othman. I'm OFS Solution Manager for Middle East and Africa, based in Morocco, in Rabat. And I have with me my colleague, Orlando Furukawa from Furukawa, who is a key account manager for the African market from Madrid. So we are a worldwide company, and we are very happy today to be with you remotely to share with you a little bit about OFS, Furukawa, and our technologies in terms of fibers, cables, and access network, especially fiber to the home tech topologies and architectures. So we would have loved to be with you at your countries, but due to this coronavirus pandemic, so we prefer to stay safety first for all of us and our customers. And we have decided to start first with this webinar. Then after everything will be okay, we can pay a visit to you and meet you face to face as needed. So I want also to inform you that we will be delivering to you an attendance certificate. So my colleague Trevor, who is based in South Africa, will get in touch with all of you for that. If you have any question, so feel free to email them, and we'll be happy to answer you. So today's presentation is going to be about OFS fiber technology. It's going to be presented by me and my colleague Orlando, and this is the agenda for this. This is the agenda for this presentation. First, we're going to talk about a little bit about the OFS introduction. Then we will see OFS fiber technology, then OFS cable structures, and last but not least, we'll talk about access network and especially fiber to the home. So let's talk about a little bit of the history of OFS. So OFS, so in 1880s, Alexander Graham Bell invented the photophone. So the photophone, for those who don't know, so it's a telecommunications device that allows transmission of speech on a beam of light, not on an electrical cable. So the experimentation was done in June, back in 1880, and where Bell's assistant transmitted a wireless voice telephone message from the roof of the Franklin School to the window of Bell's laboratory, some 230 meters away. So that was the first test that has been done using the photophone. And then in the 90s, AT&T acquires the assets of American Bell, and AT&T breakup. Lucent Technologies has spin-off Bell Labs, and AT&T's manufacturing operation is created. And then in 2001, Furukawa Electric Company, which is a Japanese company, acquires Lucent Optical Fiber business, and then OFS is created. So you can see here that this mix between the American companies, American heritage, and the Japanese heritage. So Furukawa by numbers, Furukawa Electric Group by numbers. So it was founded in 1884 with $8.9 billion net sales for the fiscal year 2019. And we have more than 52,000 employees in 122 group of companies worldwide, and we have 10 research and development laboratories. And so I said we are a world-leading designer, manufacturer, and provider for fiber optic cables and telecom solutions. So we have different locations around the world. You can see that we have OFS manufacturing. We have manufacturing in the US, in Latin America, in Europe, in Augsburg, in Germany, in Denmark. We have in Russia. And we have two manufactories in Africa, one in the top in the north in Morocco, and one in the south in South Africa. So this is very good for our customer around the world. So since we have started deploying fiber, since we have started producing fiber, over than 545 million kilometers of deployed fiber around the world, which is the equivalent of 709 round trips from the Earth to the Moon. So which is a very big number. So only in South Africa, more than 55,000 kilometers of optical fiber deployed, and 10,000 kilometers of the local production in our factory, in our manufactory in South Africa. So this is our extensive product portfolio. It is here to serve our customer worldwide, as I said. So we master the production of and the manufacturing of many part of the network, starting from the preform, which is the origin of optical fiber, to the optical fiber, drawing optical fiber. We have many designs of fiber optic cables, and we do also optical components like small splitters and small WDM module for fiber to the home, for fiber to the subscriber application. We do also optical connectivity for fiber to the home and for a solution to connect cell sites, and also some modules like DCM, dispersion compensation module, with also fusion splicing machines, and some fiber laser component and amplifiers. Let's start first with our fiber technology, and let's discuss and speak a little bit about fibers. So this is the network we support. Those are the networks we support. So we start from the transoceanic network and submarine fiber to the transcontinental and long haul network, to the regional metro network, and fiber to the subscriber. So, and this is how it looks. How it looks like the fiber to the X network. So it's a very complicated network, starting from the central office of the telco or the ISP. Can you see here, to the end customer, whether it is in a MDU, either a high-rise building or low-rise building, SFU, single family unit, or some villas, or even cell sites. So this is the FTX network is a little bit complicated, and that's why the choice of fiber is very fundamental here, not only for this network, for this kind of network, but all the other networks. The choice of fiber is very fundamental here. So as soon as your fiber is deployed, it should last for at least 30 years. 30 years is the equivalent of 4 generations of electronics. You know, today we have the GPON like access technology, but later we have the XGS PON is existing right now, and we will have NG PON 2 with 40 gigabit per second and 80 gigabit per second as a bandwidth. And we are talking about also WDM PON. So that's why the choice of fiber is very important to support today's technologies and the future's one. So for those, I think this fiber structure is very known for everybody. So it is composed by a core. It has a refractive index of N1 and the cladding. The core and the cladding, the diameter of the core and the cladding is 125 microns. And we protect this piece of glass using a coating part. Basically it is acrylate, and to have a 250 micron as a diameter for the optical fiber. And fiber is not only about glass, fiber is about also mechanical reliability. So the raw material impurities are measured on parts per billion. This is the scale how to measure the raw material impurities. You can see here this red pixel, it represents one impurity. This is a pixel on a TV, on a 1080 pixel TV, which is basically 1920 lines and 1080 columns, which makes like more than 2 million pixels inside this TV. So one impurity is one pixel, and our fiber, the OFS fiber, is roughly one impurity every 500 TVs. That means each TV is 2 million pixels. That means that our fiber is very pure. And this is how it looks like when we see it at the microscope. In the left side, you can see OFS fiber, which is based on, which is made out of high purity synthetic silica. So you can see that it is very pure. Either the core and the cladding are very pure, no impurities there. But in the left side, in the right side, you can see that some fiber made out of cheap natural quartz they have a lot of impurities, and this may cause a lot of performance issue, attenuation, PMD, a lot of performance issue that will happen, that will be seen if you use this kind of fiber. So that's why purity of the fiber is very important. Then after the mechanical reliability of the fiber, so we'll talk about attenuation of the fiber. So this is the spectral plan of wavelength. So as you see here, it is divided to many bands. We have the O band, the E band, the S, the C, the L, and the U band. And we have 3 different curves. We have the black curves that presents a high attenuation peak in the E band. So this is the conventional single mode fiber. So this peak of attenuation is due to the presence of the water molecules inside the core of the optical fiber. Then the technology advanced, and we have now the lower peak fiber, which is the blue curve. The attenuation is smaller than the black curve, but is still there. But OFS, we managed to mitigate all this at peak of attenuation. You can see here that our fiber, which is called zero water peak fiber, it is mentioned here in the red, curve. So it's almost flat, even in the E band. So we managed to mitigate using our internal process to mitigate this peak of attenuation inside the E band. So that's why it's very important when you want to spec your attenuation, or you write your specification document. It's very important to specify it for 5 different zones to make sure that your fiber will operate in the whole spectrum, not only in the C band or the L band, but will operate in the whole spectrum. You can see you need to specify your attenuation for the wavelength 1310. Let me get my pen here. So you need to specify your fiber for 1310, 1385. This 1385 will characterize the water molecule region or the E band region, and for the 1490, for the 1550, and the 1625, it's very important to specify your attenuation for the whole spectrum, not only for 2 or 3 wavelengths. So here we specify our fiber for 5 different wavelengths to make sure that our fiber is full spectrum, not operating in a specific band. For our standard single mode optical fiber, we start with the all wave, and it's even better. It is even better than the standard itself. The G652D is the standard, is the basic standard. Our fiber is 13 to 33% lower loss, and of course it is made out of 100% synthetic silica, pure reliable glass. The MFD is 9.2 seamless for splicing and testing, and of course it is full spectrum, zero water peak. Then we have the other family, it is all wave plus. It is compatible even to the band insensitive optical fiber, which is J657A1, and it has 33% better PMD than the standard itself. Then the last type of the standard single mode optical fiber is the all wave 1 fiber that can allow us to have 15% lower loss for up to 15% longer reach comparing to the standard single mode optical fiber. So we talked about the mechanical reliability of the glass. We talk about the attenuation, and now we will talk about the dispersion in the optical fiber and the PMD, the polarization mode dispersion. So this parameter is caused. By the geometry of the optical fiber. So sometimes during the manufacturing process, some supplier doesn't control the drawing process of the fiber, and this may lead to some defaults like elliptical sheet or elliptical core, or some eccentric core in sheet. So those are intrinsic parameters, but there are some external parameters. If we do some crash on the fiber, by people do curvature on the fiber, or we do more torsion on the fiber, we can create PMD. But the most important is to create a good fiber without any elliptical sheet or elliptical core or eccentric core, because as you know, we transmit wavelength inside the fiber. So, and the wavelength is an electromagnetic wave. It is composed by a horizontal part and a vertical part. So if the fiber is perfect, so the vertical and horizontal part, they will arrive at the same time. If there is a fiber which is not geometrically correct, there will be a delay between the horizontal and the vertical part, and this may lead to performance issue, attenuation, and loss of signal sometimes. So this parameter, which is the PMD, it has a limited impact when we talk about access network. But as soon as the bandwidth transported within the fibers exceed 10 gigabit per second, so we'll start seeing a big impact on the signal. So that's why I told you that today we are deploying like GPON, which is basically 2.5 gigabit per second for the downlink as a bit rate. But there are some other technologies. The evolution of this technology, we have the XGS PON, which is 10 gigabit per second. We're talking about NG.2, which is 40 gigabit per second and 80 gigabit per second. And in the future, we're talking about WDM PON. So if you have this fiber, a natural fiber, this kind of fiber cannot support the future technologies. So as OFS, so we do a process, internal process, which is called fiber spinning. So what we do is we turn the fiber when it is drawing around the vertical axis to make sure that the fiber is geometrically correct. So this is the solution we do. This is the internal process of OFS to make sure that we make the PMD parameter the lowest possible. Now I will let you with this video that shows the whole fiber manufacturing. So You have seen that fiber, the process of fiber manufacturing is not easy. It's complicated. It needs a lot of skilled people to draw the fiber. So we cannot pretend to be a fiber producer overnight. So it needs a lot of skills and a lot of knowledge. So from the starting, from the VAD process to produce or to manufacture the preform, which is the origin of the fiber, to the VAD deposition, the sintering process, the drawing process, and control of the diameter of optical fiber, to the proof testing of optical fiber at the end of the chain. So it's a very complicated, very complex process. It's not easy. So as I said, we cannot pretend to be a fiber producer overnight. So we saw how we produce fiber. We saw a lot of parameters that impact the performance of the optical fiber. And now we'll talk a little bit about the bend insensitive fiber that are basically used for indoor application. For conventional fiber, if there is a small bend on the fiber, the signal is refracted outside and the service is interrupted. But for if we use a bend insensitive fiber, even there is a smaller bend, the signal is still operating and the service is maintained. So those are very important, very useful for indoor application, especially for fiber to the home application. For the standard, so we have seen so far that in the right side we have seen the three different kind of standard single mode optical fiber. We have the all wave fiber, all wave plus, all wave 1. The all wave fiber, it allows a 16 millimeter as a bend radius. All wave plus fiber it allows 10 millimeter as a bend radius. And here we have the all wave 1 fiber. It allows 10 millimeter as a bend radius. The bend insensitive family, you can find them in the left side. We start with the all wave flex fiber. It is compatible to J657A1 fiber. It allows 10 millimeter as a bend radius. We have the second type of fiber, which is all wave flex plus fiber. It is compatible to J657A2 standard, and it allows 7.5 millimeter as a bend radius. And we have the all wave flex max fiber, which is J657B3 fiber. It allows 5 millimeters. And OFS has developed a fiber which is more performant, which is the easy band fiber. It is compatible to J657B3 and it allows a 2.5 millimeter as a bend radius. So those kind of fiber are very useful, especially for environment where we have different obstacles to make the installation or to connect the customers. You can see here, this is an example of an easy band ruggedized core, 3 millimeter ruggedized core using easy band fiber, the one that allows 2.5 millimeter as a bend radius. You can see the experimentation is 85 staples and the loss we got is only 0.02 dB. So if we do that with a standard single mode optical fiber, we will lose the signal at the first stapling. I have here a video that I will share with you that shows this experimentation in a live demo. So we have this machine here. This is at the same time is the power meter and the light source. We have the light source the light is coming out from this port, and the technician here is trying to stapling the cord, the same easy band 3 millimeter cord, and then he will do some corner here, and the same tool we will read the power and it will display the loss, which is here in the top right corner. So up to now it's only 0.01 dB, and the technician will continue stapling the cord and do many cornering just to simulate indoor installation. Even a 90 degree angle. So here we don't lose any signal. You see, it's 0.1 is almost null. So after many cornering, after stapling, so So the technician will add an additional weight on the cord, and the loss is almost zero. It's 0.02. So if we do that with a standard single mode optical fiber, we will lose the signal for sure. So this is an experimentation that shows that the easy band fiber is very strong, very robust, and the installation of those kind of fibers is seamless to an electrical cable, to a copper cable. We don't lose a lot of signal if we're using high performance patch cord or cord using easy band fiber. So then, and we have besides the standard single mode optical fiber and the band insensitive fiber, we have different kind of fiber selection depending on the application, of course, because we need to select the application to select the right fiber for your application. Here, for example, it's for long haul network, for network that exceed 1000 kilometer here. So we have different kind of fibers, J654.B, J652D, and J655C, depends on the application. So depending on the application, you need to select the right fiber for the right application. Here's a good example that shows that the choice of the application, choice of the fiber is very important, and this a good choice can save a huge cost or a huge amount of money. For example, here is a link between Brasilia and Curitiba in Brazil, which is 1,300 kilometers, which is basically the same distance between Johannesburg and Cape Town. So if we use the standard single mode optical fiber, which is the J652D, so we need a regenerator, electrical regenerator in the middle to regenerate the signal. But if we use the fiber, the large MFD, large mode field diameter fiber, so which is a TeraWave ULL, so we don't need any electrical regenerator here between the two cities. So knowing that the regeneration one wavelength, it costs roughly $40,000. And also a link like this is not only we don't build only a link to transport one wavelength, but we build a link to transport many wavelengths, like 10, 20, or even 40 wavelengths. So imagine if we have 40 wavelengths or use J652D, so we need to regenerate 40 wavelengths. So imagine the cost of the electrical regeneration here in the middle. So that's why I told you that the choice of the optical fiber is very important, and it can save a lot of money during the rollout. Those are fiber, for example, for regional metro utility wireless backhaul for the network from 60 to 1000 kilometers. We can find here the J654B, J652D could be used as well, depending on the application, J655C, and J655E. So we have different kind of fibers depending on the application. Here, for example, for network up to 60 kilometers, for home, for FTTX home business cell sites, it's basically here band insensitive fiber A1, A2, and also for high density application, it is basically band insensitive fiber. You can see here the A1, the A2, and the B3 fibers. So today, the limitations that are very known for the fiber are attenuation, chromatic dispersion, and PMD dispersion and non-linear effects. So there is a solution to mitigate all these parameters. For the attenuation, for example, you can use the fiber with lower attenuation, and you can optimize your network. Or if you don't use the good fiber, you will invest on amplifier. You will need amplifier, electrical regenerator. For the chromatic dispersion, yes, there is a solution to mitigate the issue and the problem. So the solution is to use fiber with low dispersion coefficient, or to invest on compensation with dispersion compensation module. So the PMD, yes, there is a solution. So use a fiber treated with spinning, like I have shown you in the slide before, to minimize the risk. And also for non-linear effect, yes, for sure there is a solution, is using fiber with high MFD or large MFD, a large mode field diameter. If not, if you don't use this MFD, you will still need to use power control and amplifiers. So those are the limitations that are very known today for a fiber transmission. I said attenuation, chromatic dispersion, PMD dispersion, and non-linear effects. So we talked about fiber and about parameters that could impact the transmission and the performance. Now we'll move to the third part, which is OFS cable structures. So there are many types of construction. They are developed to best fit the application and based on international standards for mechanical and environmental requirements. So let's start with the loose tube structure. So those are cable that with loose tube, either with 12 or 24 fibers per tube. You can see here a tube filled with the gel or not or dry, with 12 fiber here inside. The cable could be jelly filled, dry core, or totally dry. We can go up to 864 fiber per cable, and it is used for external network for outside plant cable, and the cable could use either the 250 micron fiber or the 200 micron fiber. I will talk later about the 200 micron fiber and its benefit. Here's one cable design. It is called the Media FX. Is a micro cable. It is composed by 12 tube, as you see here, and inside each tube there is 12 fibers. All those tubes are arranged around the central member that gives the strength to the cable, and the outer jacket is a polyethylene jacket. This is a 144 fiber cable. This is called the Media FX cable. Then there is the tight buffered cable. So here for this cable we use the 900 micron fiber instead of the 250 or the 200 micron. So those kind of cable are used for transition from internal to external, or they are used for internal use, like data center connection inside data center and so on. This is an example of how the 900 fiber are organized inside the cable. Either we can organize them around the central member like this, or we can put them inside like a tube, and all those tubes are arranged around the central member. So it depends on the design, but the fiber here inside is 900 micron. So we talked about 200 micron. So the 200 micron fiber is here to densify the number of fiber we can put inside the same diameter of the cable. So the core here, the core and the cladding is the same. The diameter is 125 micron, but we reduce the coating part, the diameter of the coating part, in order to densify the number of fiber inside the same diameter of the tube and same diameter of the cable. So this is why we are using nowadays this 200 micron fiber as a way to densify the number of fiber inside the core. So you can see here that inside the same tube, here we have 12 fiber, 250 micron, and inside the same size of the tube we can put 24. But here there is an issue. We will have like two different colors. We have red and red, blue and blue, yellow and yellow. So how can we differentiate between the colors inside a tube with 24 fiber? So the answer is, so we use ring marking. So to make the differentiation between the two red colors, so one color is without any ring marking, and the other one is with ring marking, in order to differentiate between the fibers. So this is 200 micron fiber, and this another way to densify fiber is the flat ribbon. So the flat ribbon is 12 fibers. They are all stick together on all the length in a way to form like a flat ribbon. And in that way we can produce or can manufacture cable can go up to 1728 fibers per cable. The new generation of ribbon, it is called rollable ribbon. So those are 12 fiber, and they are not sticked in the whole length, but they are sticked in a specific way, specific point, in order to form like a spider web, like you see here. So like this ribbon is rollable, is easily rollable, and it can optimize the space inside the cable, and we can produce or manufacture cable that can go up to 3,456 fibers in less than 3 centimeters. So this is a huge number of fiber in a very small diameter. For sure, you should have asked this question: why we need all this amount of fiber? Of course, we need this big amount of fiber, because look at this diagram, at this graphic. On the left side, you see the 4G topology. You can see here that the cells are connected to active equipment at the bottom of the cells, and we need some from 50 to 100 fibers at the front hole from the cell to here. And of course, we still need fiber from the active equipment here, from the radio equipment here to the central office. So we need like 200 from 72 to 288 fibers. But the 5G is different. It's a new topology, a new architectures. So all the cells will be connected straight to this cloud RAN, which is the cloud radio access network, through fibers. So we don't have any processing equipment, any active equipment at the bottom of the cell sites. All the cells will be connected straight to the cloud RAN using fibers. And you can see that the huge amount of fiber we need in this transport network, this trunk network. So we need from 864 to 1728 fibers for this kind of network. And it's not only that, because there is 5G and the future is smart cities. There are many applications of the smart cities. We're talking about fiber to the home, and we're talking about dark fiber. So you can imagine the number of fiber needed in the future for in the access, distribution, and the transport network. So, and one of the other solutions to densify the fiber, especially in the access and distribution network, is the micro cables. So micro cables used with the microducts are very useful because they are small. You can put a lot of fibers in a smaller diameter, and it can allow us to optimize the civil work, the existing civil infrastructure. So the application of the microducts cable are very huge. We can use them as an override in an override application. We can install them in an existing conduit with existing cables, or we can install them previously unused duct microducts, or we can think if we are building a new project, we can put different microducts and we can use a greenfield, the grow as you go application. So for example, we can put 3 ways microducts, and we can use only one microduct and blow a cable in it and keep the other for the futures. The advantages are very huge because they have many advantages: materials, workforce, and financial. So reducing the cost of materials for cables, sheets, splices. For the workforce, the cable could be blown to a longer distance. That means that we need a fewer junction point, and we need a smaller handhole, smaller junction splice box. And for the financial, it's an opportunity to increase the capacity whenever there is a change on the technology, and whenever we want to make upgrade on our network. That's why we use the micro cables with the microducts. And the microducts are very today, because the space today is like a premium, so it is limited and expensive. Sometimes we found difficulties to obtain the permits, and the civil works also are very expensive. That's why nowadays some of the telcos and the ISPs are looking for other alternatives like sewers, gas, and water pipe to put the cable in. But this micro cable and the micro cable and microducts gives us a great opportunity to optimize the space and the existing civil infrastructure. Look at this comparison between a standard cable. So this cable drum is head height, while for a 6 kilometer length of a micro cable is only a waist height. So you can imagine the size of the warehouse you need to store a standard cable comparing to a micro cable drum. So this is a standard traditional design. The 144 6 kilometer of the cable is 850 kilogram. Then if we use the mini cable generation is 565 kilogram, and the new generation of micro cable is only 240 kilogram. So you can optimize a lot in terms of warehousing, in terms of transportation, and you can make a lot of optimization using only micro cables instead of standard cables. Also, the cable is smaller, and also the infrastructure is going to be smaller as well, because you're going to use smaller handholds, smaller manholes instead of the bigger one for standard cable. For the civil work is very easy as well. So you can see here the machine at the right side. This is what we call the nano truncheon. It's 7 to 30 centimeter depth, and it's 5 centimeter width only. So the civil work is very easy. It is done by machine and is not disruptive. Look at here. So in the left side we have nano truncheon technology. It's 5 centimeter depth, and at the right side we have micro truncheon, which is 15 centimeter depth, 15 centimeter width. So you can imagine also the amount of optimization on the material to repair this digging into the road for the nano truncheon comparing to the micro truncheon. Here's an example. Here's an example of Media Micro GX. You can see, look, remember remember this number. You can make a 288 fiber in 9.6 millimeter if we use a 250 micron fiber. But if we use a 200 micron in this, you can keep the same number of fiber, 288, but we can do that in 8 millimeter only. So we gain like 1.6 millimeter only using 200 micron fiber instead of 250 micron, and which this is very, very useful. Also, for the blow-in performance of those kind of cable are very important. So if we blow 288 fiber, so we did an experimentation. So we blow this cable in to 1,900 meter in like roughly 30 minutes, half an hour, which is a very good number. Of course, we follow all the performance, all the IEC performance from tensile, crash, repetitive bending, torsion, bending, and kinking. So those are the IEC standard we follow. So we talked about a way to densify the cable optimized on the civil work. Now we will talk about a cable type or cable structure that allows us to deploy very quickly because we're not dig into the ground, because this kind of installation is aerial. That's why we this method is very spread, especially in Africa. It's very used, very common in Africa, to use ADSS cable, all dielectric safety port. We have different design, either loose tube or ADSS ribbon cable, and ADSS applications are very we have different kind of application. We can use them with the distribution poles. It can be placed above or below the neutral in accordance with the NESC, and especially it is useful for FTTX trunk or distribution network, which is which is used on distribution pole. It can be used also on transmission line for a backbone to connect between cities, and also it can be used inside the conduit, in a conduit like a regular cable. So each cable designed is specific to an area, specific to a customer, specific to an environment. So because we ask, when designing the cable, is design specific. So what we ask our customer to provide us when designing the cable is the fiber count first. Then we need the worst case environment loading condition like ice thickness, temperature, safety factors, and also the maximum span, which is the distance between the two poles. And of course, we ask our customer about installation sag percent. If not, we assume that is 1.5%. And of course, we ask for the line voltage to check whether we need to add the tracking resistant jacket or not. So this is the cable. As soon as it's installed, it is elongated like this, but it is kept in a safe conditions. So as soon as the cable is installed, so it is acting like a spring. So after if there is wind, and if there is some ice, if there is the max rated cable load that the cable was designed for, so there is no issue here. So the cable is acting like a spring. So if we exceed this parameter, that is very important, the cable can break and the cable can break. But if we are in this zone, this green zone, so we are safe. The cable here is acting like a spring. So this is how the ADSS cable is operating in the field. So we talk about a lot of fibrous cables, but I want just to remind you that choosing the right fiber and the right cable can save you a lot of money when deploying your network. But one thing I want you to look for in your fiber deployment is the service convergence. So when deploying your fiber, think about that this cable should support all or should transport all the data from all the application in a city. Think about the smart cities, think about the IoT sensors, think about fiber to the home, think about the 5G which is coming, think about the dark fiber if you want to make your business plan wider, and think also about real-time applications. So think about the service conversions, which is very important when deploying your fiber. So now we move to the last part of the presentation, and it's gonna be handled by my colleague Orlando.
Hello. Well, let me take over of the presentation. Well, hello to everyone. Now we're going to start to I'm sorry, now I think my microphone is okay. So I'm going to start to talk about FTTH specifically. So Otomona has introduced us to all about fiber, the different kind of fibers, the applications, how to deploy it. And now we're going to integrate the cables to the connectivity. Connectivity is boxes, splitters, drop cables, all the accessories involved in a FTTH deployment. Well, so this is going to be the focus today, FTTH, specifically GPON networks, not only deploying fiber itself, but how to deploy fiber to the customers. Because, well, as you could see, fiber is not something new. It's from the 70s, and actually we are already using fiber massively, and we have been deploying fiber to customers using point-to-point networks. So probably most of you know that we can have dedicated links. This is the common way to say point-to-point networks, which basically deploys fiber from the central office to a subscriber using a dedicated link. So financial institution, hospitals, government institutions have been using this kind of technology. But if we think about massively deploying fiber to regular customers like we are, to have fiber at your home would be impossible and unsustainable to use this kind of technology. Because, well, even back then, it was necessary 2 pairs of fiber. So for each customer, you have 2 pairs of fiber, and part of the central office, the equipment also dedicated to that fiber. That's why we say dedicated link. So basically, not a cable, but you have 2 fibers for each customers in one part of the equipment for each customer. So if we think about a whole city, every home of that city having 2 fibers and one port in the central office would be impossible to massively deploy it. Can you imagine a central office with, for every single home installing fiber, you having a equipment over there? Would be impossible because the higher energy consumption, the dedicated bandwidth, the amount of fibers of those cables, so bigger cables, heavier hardwares, they are going to be harder to install. So all of that would be impossible to deploy. So that's why we created the PON. What is a PON network? It's passive optical network. So we basically introduced a device called the splitter, which just splits the power, the fiber power, the optical power, sorry. And now, instead of having 2 fibers for each customer, we will deploy just 1 fiber per customer, and Now this splitter is dividing the OLT, the center of support, in 64 and up to 128. So this is the minimal requirements that you have here in this slide. But we today can also divide it by 128. So for each port in the central office, now we can reach 64 or up to 128 customers. And those customers will have just one fiber reaching their homes. And those unique fibers, they are not from the central office. They are from a midpoint in the network. So the infrastructure from the central office to this distribution network, let's say, and then we have the examples here, it's reduced dramatically. So we have just one fiber now, let's say, roughly say, for up to 64 and from 64 up to 128 customers. Basically, this is summarizing what is a PON network. The PON network is basically just a transportation network, which converts in the central office the electrical sign, right? So you have your servers that are going to connect to be connected to your OLT as electrical sign with patch cords, for example. Then we transmit it, and then the other side we have to do the other way around. So we receive the optical power and convert to electrical power. Then we connect our notebooks, our set-top boxes, with routers, our TVs, and then they are electrical again. We have the patch cords, and it's a regular protocol, Ethernet. So everything that's IP can be transmitted in this network. So that's why Otmani was saying that it is important to think about a convergence of services, because using the PON network and the fiber, we can have any kind of services running through that network since they are IP. So it doesn't matter if it's just internet or video or telephone. We can connect cameras, sensors, everything which is IP can be connected in this network. So what we are talking here is a network that doesn't only connect homes, regular customers like we are seeking for internet, but this very same network can be monetized by connecting different kinds of customers and sensors and ideas. So since it's fiber and we have this almost, let's say, unlimited bandwidth, we could aggregate the services on the top of this network and take advantage and do not have layers of network when we are talking about deployment. Well, this is the basic standard of what is a FTTH network and how it looks like. It's pretty simple. We have the OLT on the center office, right? Each port of this OLT can be divided up to 64. What I'm talking here is the minimum requirement of the standard, right? So let's imagine Furukawa wants to deploy a new product, a new OLT transmitter. This is the minimal requirements we have to follow. As I was mentioned, it depends, it varies to the manufacturer to manufacturer. It could be even better. So speaking about the minimum, we have the OLT on the center office. We can divide this port up to 64, right, in a range of 20 kilometers. So it's a radius. So if you imagine your center office is like a circle, right? So we have a radius of the 20 kilometer to reach the last customer, which is pretty good if you are thinking about a city. 20 kilometers, it's more than enough to cover huge areas, massive areas. And of course, we will not have just one central office to cover a city. So if you imagine isolated POPs that, not isolated, actually they are singular POPs that are communicating between them through a metro and a core network, you would have a coverage throughout an entire city. Some customers, and we do have that, we have already the lasers, the power budget of the lasers have been improved, so we can reach up to 40 kilometers, having to 128 divisions. So it depends. Of course, you always have to respect the power budget, so the data that the transmitter has, and this is calculated when you have the design of the network. So sometimes if you divided more, your distance will be shorter. If you are dividing less, your distance can be longer. So it's a matter of combining both. But as I said, in a city, or probably you will not have this problem because you have different pop-ups for regions. So the distance of 20 kilometers is more than enough. Then it allows you to divide it more. So since you are dividing the same port more, it means that that port costs less per customers. So this is an important data to have considered. So it will increase the cost per customer, and you're going to have more revenue since you are spending less. Well, how we divided this network, how we make this, as you can see here, we have two levels of splitting, right? So the first one and the second one. And the splitters, they are components that basically just divided the optical sign. They don't have any logicals. That's why we call a passive optical network. So it's a very tiny, I wouldn't say equipment, it's a very tiny device that just is like, let's say, pipes. You know, you have a bigger pipe of water, and then you're going to divide it, and then you use, let's say, this is splitter to just divide the flow. So you are dividing the optical power. So you have from up to two, you have from 2 splitters, which means 1 entry port and 2 outputs. So 1 2, 1 4, 1 8, 1 16, and 1 64. So how you arrange that in a design, it depends on your network, the density of the customers, the take rate you are intended to do. But in generally speaking, the most useful and the most applied rating split is 1 per 8 and 1 per 8 again. So you have the 64 here, as you can see on the right side. So first you divide it by 1 per 8, and then again another 1 per 8. It allows you to spread your network through the area, right? So, because can you imagine if you have 1 per 64 splitter only, it would be almost the same of doing a point-to-point network. So from a point you have 1 fiber reach each customer, so which is not good because your fiber accounts of the cables will be higher than you need. So that's why we place these splitters in the strategic positions of the network when you are designing it, to reduce the fiber count on the cables, on the distribution cables, and let those splitters as close as possible to the customers in order to have this cable connecting the splitter to the customer as short as possible. So here is basically an idea of how a very simple idea of how a FTTH network is deployed. So you have the central office, then you have the cables leaving this central office, then you have a first level of splitting. This splitter is feeding the second level of the splitter, and the second level of splitter is connecting the homes. As I mentioned, we try to place the second level of splitting as close as possible to the customer, right? So in order to have this drop cable, this last mile cable, as short as possible. Why? Because you want to connect the customers as fast as you can, because this is always a cost. So it's always is a combination of product and designing, aiming to have a faster installation, and also aiming to use as less as fiber as possible on the cables, because it reduces the size of the cable, the hardware is used, the time of installation, all of that are operational costs. So we also aim to reduce operational costs when we design a network, right? And here we have two applications which are SFUs, so single units, right, like homes, and we have like homes, stores, villas, gated communities, and we also have MEDUs, which here is written by FTTH, like fiber to the apartment. When we have buildings, and in those buildings we have, let's say, single units sharing a common infrastructure, right? So the products we apply for These two situations are different, and I will explain later. Well, since we have an idea of how it's a network, we are going to into details how to deploy it. So we have architectures of networks that are being used in the last 15 years. Basically, we have three of them: a centralized one, local conversion, and distributed splitters. I already have spoken a little bit about distributed splitters, but I want to have give you the examples of the other two, and why we are now in the phase of distributed splitters. So the first one is centralized. It means that we are placing our splitters here in the central office. Why we would do that? In the point-to-point solution, we have one port of the equipment for each customer. If you will want to save in the equipment energy consumption, equipment storage, let's say civil works, all of that, we could use the OLT in the central office, right? When I mean OLT, you can just translate as optical transmitter. It's basically that. So we can place this OLT in the central office and divide the ports. At least we're going to have a reduction in the cost per customer in the active side of the network. In the passive side, when I say passive, you can translate it as cables, cabinets, splice closures, all of that which is not connected to a power outlet, let's say, the splitters, wouldn't change in this situation, right? So from the central office, we would have all the cables, all the fiber account, better say, necessary to connect that customers. So basically, we would have almost a point-to-point network, talking just about the passive side, which doesn't bring too much pros, right? So of course we are reducing the cost per customer in the equipment, but in the network deployment, we would keep the same fiber accounts. We would have the same hardware and everything. Just an example that works. When it works, let's imagine a gated community. When let's say the fiber optical network would represent nothing comparing to all the other infrastructures they are building, and they want to let it ready when the customers start building their homes, let's say. So of course it will not impact it, and it's a very unique case, which is better you have all deployed and then you just connected the customers to the central office, but it doesn't apply to a city, it doesn't apply to a, let's say, regular condition. So we evolved from that to what we call local convergence architecture. So the idea is to place the splitters out of the central office, right? So at least we have the feeder cables reduced. So all this metro and core network would be relieved of these massive fiber accounts coming from the central office. And then now we have a local convergence point, which is a little closer to the customer with the splitters. So let's say we solved halfway of the problem. So half of the network will be already with less fibers, but half of it will still have large fiber accounts. This local convergence architecture, was developed also because at the beginning of the FTTH deployment, the equipments were really expensive. Just so you know, when we talk about 15 years ago, 20 years ago, the OLT port cost around $10,000. Now it costs around $800. So dramatically reduction. Back then, since the equipment were very expensive, so this cost per customer would have to be, let's say, as precisely as possible. So when you divided one part of the equipment, you really wanted to connect the customers to that port because it was really expensive. So you could not afford to have parts of equipment like with no customers, right? Because it was a great investment. So the cabinet came to that. So you deploy your network, and the cabinet will use it to patch the customers. So you have the first part of the OLT, right? Since it was very expensive, you must to connect 64 customers in that port. So you route the customers to that port in that cabinet. At the moment you have the next 64 customers, you buy this OLT port and then you start routing them. So to make the OLT investment feasible over the time. But since now, and another thing, the cabinets were really expensive because we are talking about a product which needs like IP67 grades of protection. It's on the street, so sometimes we also have this problem with civil works. We have problems with vandalism, all of that, which makes, let's say, the solution expensive in OPEX as well. So since now the equipment have been the price have been decreased a lot, let's say, we are able to do a complete distributed splitter architecture. So we have now two levels of splitting. So from the central office, we have a first level of splitting, and this first level of splitting will feed a second level of splitting. Why just two levels? The splitters are the, let's say, the component, because we have losses, right? So the cable has losses powers, the connectors, all of that, but the losses are concentrated on the splitters. We could have one more splitter and have this part of the network divided by 256, for example. In theory, we can do that, but the problem is the laser would have to be stronger, and if the laser is stronger, it's more expensive. So you gain from one side and you lose from another. So it's a combination. That's why it's 64 and 20 kilometers. Because if we do the power budget, and what is the power budget? We need a minimal sign on the customer side to the equipment communicated to the transmitter. So when we add these losses, and it's two levels of splitting, we can cover up to 128 customers or 64 customers within 20 kilometers. And this is like our optimal combination of distance, laser budget, power budget, and splitters levels. So we don't need more than that. And if we increase those distance or the splitting divisions, that we will bring back that problem of the equipment being expensive. So, and 20 kilometers is more than enough when we talk about in a city. Of course, there are situations, for example, rural areas that we need to extend the network, but we are talking here about the 95% of the cases, 90% of the case. For those isolated applications, we have amplifiers, we have different topologies, we could think differently. But what really matters are cities and the telco operators. So that's why this is the most used network topology right now. So the implementation cost is lower because you don't have all that cables, you don't have that cabinets, the prices of the equipment now has decreased, and you can have your coverage much well and much more distributed. Well, why 1/8 splitters? This is the explanation here using the MDU example. Let's imagine we have a building with 35 customers, right? So on the first situation, if we use 1/64 splitters, because you can say, okay, I can put 1/64 splitters in the base of that building and it's covered. The problem you lose is 24 customers in your equipment. Okay, you can try to optimize and have several combinations. I could use a 1/32 splitter and also add 1/4 splitter. And you will lose just one customer. That's right, but you can't design for every building in a city or every area like in this specific combination, specific looking into details. So it would take too much and your design would be a mess. But if you apply the third mode, which is the single modularity, you can place 5 splitters of 1/8, and at the end you are losing just 5 customers in your central office, let's say, in that OLT port. But your design is much simpler. You use just the same design of the same splitter, so your technicians will be trained to use the same product only. Your designer is going to design according to that topology. So all that you are saving by designing, it's covering these 5 customers that you mobilized on the central office. Here we have the diagram which explains better. So the first one is like, okay, I have homes and I have a building. So I will use first 2 levels of splitting to the homes, but I will use 1 splitter already into the building. So this is the complicated scenario I mentioned. So the second scenario right below, we have the first level of splitting being shared by buildings and by homes. So as you can see, you just place the number of splitters you need in that building. So at the end, there is no differentiation of SFUs or MDUs. You just place as much as splitters you need in the base of the basement of that building. So making the designing much easier. So you treat each customer of that building as a SFU customer, but at the end you just aggregated the splitters on the same box and the basement of that building. Just that. So it's bringing the design to the very same level, independent of if the customer it's the SFU or MDU. Well, now we are going to jump in the product line. So since we talked about fiber, and now we talked a little bit about the designing and how it's the topology of a FTTH network, and I introduce you this splitter equipment. Let's talk about the products, the connectivity products that wrap up the solution. So Furukawa, today we have end-to-end solution. So we are one of the, actually we are the only one that can under our own unique brand to deploy equipment and also passive equipment, passive components. I'm sorry. So we have from the central office to the termination network all the components you need. So it's possible to build 100% Furukawa network, all the equipments, transmitters, optical receivers, boxes, cables, splitters, whatever you need, patch cords, pigtails, all of that we can source under the just one brand, which is it's Furukawa Electric Group. I'm going to start by segments of the network. So let's talk about first the central office, then the distribution network, then the access and the termination network. So I will not talk into detail each product. So I will just we are going to have an overview of the portfolio, and then we'll talk specifically about 1 or 2 new products we have. Of course, later on you can get in contact with us, and then we can discuss on details. So the central office, we have basically the active equipment and the passive equipment. The active equipment are the optical transmitters, the OLTs, and the passive equipment are all the racks, cable managers, ODF trays, small connectivity as pigtails and patch cords. So we have a completed line of central office products here, the OJFs, the racks, and also the shelves. In some conditions, in some projects, the splitters are concentrated in the in the central office. So we have this all LGX splitters. So they are assembled and they are special to be on the central office, but just in some special conditions. Here we have in details the OLTs, so those are the transmitter. We have from 512 customers up to 40,000 customers OLTs. So it depends if your project it's small at the beginning or is starting already big or is going to be big on the future. We have the transmitters specifically for each phase of the deployment, starting small, even reaching, let's say, telco standards of transmission. And the ONTs are the let's say optical receivers, which is going to receive as optical sign and then we transform it to electrical again. We have several models of that. From the simpler, which has just one port. So imagine you just connect, let's say, a router or a computer or a camera, and we have those which have all the services you need: telephone, internet, Wi-Fi, all integrated on the same equipment. So it depends on also the project and the applications you are going to give. If it's a camera, you don't need the Wi-Fi, so you use the small one. If it's a residential and you also need the Wi-Fi, video, we will just use a different model of receptor. Well, talking about now distribution network. Distribution network, actually Ultimani has covered it because basically are the cables and this optical closures. So there is nothing much new in distribution network because, as I mentioned, we have been deploying fiber since the 70s. So the distribution network is basically same like cores network, metro networks. You don't need much different from cables and optical closures. The difference here, in some cases, as I mentioned, we have the cabinets and the pedestals, and we do have the splitters. So the splitters, this is the, let's say, giving face to the numbers. So those are the splitters. They are very small components which are basically just dividing the power. So you have one fiber and X fibers, one fiber as an input and X fibers as an output. Now we are going to the access and termination network. This is the segment of the network which requires most attention because the OPEX costs are basically in this part of the network. Because you build the network and your boxes are waiting for the customers. So it's a daily operational costs involved in daily basis. So your technicians has to go and connect to the customers day by day. So that's why we invest, and that's why all the new developments are done in this segment. So why? We're trying to make the boxes as cheap as possible and also as fast as possible to install. And also the access network is really tricky because it's variated from country to country, from region to region, sometimes even in the same city, in the same country. So the box applied here in Madrid when I'm based is not the same that is applied in Rabat where Ultimani is based. So we have also to adapt our solutions. But the central office and the distribution network doesn't change much, right? So we have the access and termination network for homes, SFUs, and we also have the access and network termination for MDUs. I will start for SFUs, which makes things easier to understand. So here we have the network access point closures. So basically we call sometimes NAP closures, CTO closures, and it depends on the solution. It can use field installable connectors, those are on the left, and also hard-end connectors, which are pre-assembled from factory. So it's a connector that the cable comes with the connector and just to plug it into the customers. The optical cables here, they're quite different because what do we need here? We need speed of installation. So the cables are as tiny as possible. The fiber also B3 or A2 standard. So Ultimani has explained the standard of fibers. Why they are like that? Because when you have to connect a customer, the environment is pretty aggressive. You have a lot of corners, you don't have too much space. People doesn't want to see the cable in their home, so you have pass-through duct. So the fiber band sensitivity is really a matter here, and it's really important. And we also have the accessories like connectors, splitters, for that kind of for that part of the network as well. What we're trying to do is this: reduce in capex, reduce the costs on OPEX as well, create products with simpler planning. So in that moment we are designing the network, it is important that the products always allows a simpler design and the on-demand investment. So it's important to have solutions that you can start that you deploy when the customers are being connected. So you don't have to invest and freeze your money, right? And just get it back when the customers are being started. So if we can, like, let's say, make this as flat as possible. So at the moment you are installing the network, you are already connected, the customers would be the best option. So the first thing new we have, and which is different, so it's the easy connector. It's a field installable connector. So because when I was talking about operational costs, can you imagine if you have to splice every single customer at the moment you have to install it? So you have to open the box, clean the fiber, open the cable, splice it, and then move forward to the next customer. It will increase the operational costs. So now basically almost all the operators, almost all of those that are in the not in the initial stages of deployment, they use connectors or they use pre-terminated drop cables, those which has a connector in its end made on factory. Why is that so? It's because they want speed of installation. So at the moment you connect a home, you do it as fast as possible, and then you move to the next one, right? Because you want the revenue, the revenue increasing, and you have it by connecting customers. So the first one is the easy connector. We call it easy connector. It's a field installable connector. So the difference here, it's in here, the gel. So sometimes people think about this connector as a regular connector, as a patch cord connector. It is not. So it has a very unique and different gel inside, which allows to sustain vibration, temperature, because we are talking about a connector that's going to be changes of temperature, is going to be in an outside box. So this is a very, let's say, the technology involved is much more different from a regular patch cord. So those connectors are really, really special in terms of technology. The next option is to use those connectors we just plug and play. So in this situation, you don't have even to assemble the connector in the field. You just go and plug and play. So you plug the network side, let's say, which is this one, and then you have another end that you use that field installed connector to connect the customer. So the cable comes with one end with the connector and another end it's loose, and then you install the connector on field. Why one end is loose? Because if you need to roll out the cable through pipes, would be impossible with a connector like that. But you are at least saving time from the net closure side, because you don't have to even to open it. You just plug and play. You just connect the cable and move forward. So the idea here is like that: reduce splicing. So the splice machine also is a cost involved. Sometimes it's a heating cost. Sometimes we just compare bill of materials, right? So this bill of materials is cheaper. I will go into for it. Sometimes it's a mistake because we have a lot of heating costs. Basically, these heating costs are operational costs. So the idea of connectors or field installable connectors are reducing the splicing, so you don't have to invest in splice machines. The hardwares, the MENSA, the pole, the label skills are not that doesn't to be that high. So you also are reducing the OPEX in that side, and also the hardware. So basically, for those drop cables, which are tiny and lighter than regular cables, the hardwares are plastic, which are much cheaper. So they are smaller. So also the visual impact is reduced. So the customers sometimes appreciate that as well, the visual impact of the installations. So the idea is to save in operational costs. We are moving forward to the MDU solution. Basically, it's the same idea, but for buildings. Here we have the several boxes. I will not get into the detail of those boxes. So depending, we have the floor boxes, the basement boxes, the optical cables, the riser cables, which runs the fiber through the building, and we will talk with a special detail for this Invislight system, which is basically gluing the fiber through the pathway, and well, we want to see so basically this is the topology of deploying fiber into a building. So you have this entry point which has a box which shelters the splitters. Then you have a riser cable distributing the fibers from the splitter into the building, and then we have the floor boxes which are going to distribute the riser cable to the premises, right? So the idea here is again activation to being faster. So applying connectors and the right cables, we can reduce in 51% of the fiber installation. We also have the on-demand solution. So you start connecting your customers and buying the products only when you have the customers at the network already. And this is the last solution we have is the Invislight solution, which is basically an invisible fiber that applied for that situation. You don't have any infrastructure on the building, or let's say it's a building that cannot have any civil work added. Let's imagine a museum or a church or something that it's a monument, something like that. You can also apply this situation, this solution. So basically it's this, it's a pigtail, a very long pigtail, roughly say, which is glued to the corners on the wall, on the floor. Well, and this we have in a video which explain much better. Well, we have a problem with the video. It's on loop. Let me try to see if I can move it forward to the end. No. Anyway, we can share it later. Just to concluding, all of that we are presenting here, the products, the solutions, well, all this theory and also all the products. We are more than manufacturers, so we don't have this sales system as a catalog, like which after this presentation you guys get in contact with us and well, I want to some pieces of this part number or the other. The idea we have is to create an ecosystem, and by supporting our customers during all the phases of the project. So we have these engineering services, which are basically a consultancy that we can offer. We have all the trainings, we have the even warranty, extended warranty in some cases, installation supports, all of that even before the project, even before the purchase. So consulting projects, we offer for free and no commitment of the later purchase to analyze some areas, doing a study to deliver a bill of materials and a prep project, let's say, with the topology, with design, with the most optimized insights. So we have some bill of materials generator when you want just to have an idea of how much would cost FTTH network. You just can input the data and it will generate. We have tailored products, so some of our customers need adaptations because of the conditions of the countries of the installation, so we also can work on that. And we have these training capacitations. Well, this first one is online of those trainings, but we also have trainings on projects, trainings installation, webinars like this one, webinars more focused in some situations that the customers demand. We have training certifications for installers, for integrators. We have trainings centers, and we are still open more of them. So the idea is to spread the knowledge and working close side by side, close to our customers, not only this catalog system of sailing. So the idea is to generate this ecosystem. Here we have all the trainings we have, the certifications. Well, we can check also in our portal and our website. And basically is that. I don't know if Otmani wants to have some final words. It's up to you, Otman. Well, thank you very much for your time.
So thank you, Orlando, and thank you all for your time. So we reached the end of this webinar today. I would like to thank you for your time today, and I hope that you found the answers to your questions about fiber and fiber technologies during this webinar. So if you still have some questions, fill out please the form on the right side of your screen, and please make sure to include your first and last name and email before you submit. And I would like also to add that in the near future, you will also receive through email a certificate of participation in our webinar and a link to the video of the presentation. Thank you all, and thank you for your time.